All right. So let's discuss the calendar. We're not changing anything. So today is, well, it's the 1st of September. Get that rent check in, right? Tuesday, September 1st, it's day 5. I'm going to discuss sections 1.1 and 1.2 on functions and their graphs. Now, technically, these sections will not be due this week. So the homework for chapter 1, which is on my website, the homework for quiz 1B or whatever, I'm going to cover that material today, but it will not be due this week. It'll be due over here, the day, September 18th. But I'm going to get a head start on chapter 1, all right? And then we should have about 30 minutes at the end of today when I'll start to take homework questions from the class. And then I'll have much more time on Thursday taking homework questions from the class. And also we'll do section 1.3, which is a great section about the gallery of graphs. So you don't have to point plot from scratch. It will be a benefit to attend, and you can learn how to graph things without having a point plot. Okay, so a great section, 1.3, lots of good pictures there. And of course, to answer whatever homework questions you have or any questions on Thursday, your homework is due Friday at the end of September 4th. Basically 11:59 p.m., midnight, right? End of the day, Friday. That's when the homework's due. Okay. No rush today because I have this gap at the end. Any questions before we begin the videos, the chapter 1 videos? Go ahead and turn chat on. Let's see. Yes, everything for chapter 1 is on my website. So that includes the chapter 1 notes, and that includes the homework for chapter 1. It might be called the homework for quiz 1B or something, but yeah, the notes and the homework are on my website. By the way, chapter 1 is my last really nicely typed set of notes. Chapter 2 on, they're typed, but they're really old, like board notes. Okay. Some of you might benefit more from them because they're more concise, actually. By the way, I'm going to go ahead and mute the class. All right. Any other questions? Okay. Right. So, yeah, Joshua posted the link here. Right. So here are the notes. For the homework, though, for chapter 1, which you can get a head start on. Yeah. It's homework assignment 1B. That's for chapter 1. So that's where you get the homework and answers. And actually, what I should be saying is, hey, you're keeping up with the class, right? So you've basically done your chapter 0 homework, right? So I should be telling you folks, well, yeah, you can get cracking. You should get cracking on the 1.1, 1.2 homework, but that's not due this week. Still, I should encourage you to keep up, right? So I do encourage you to get cracking on this as soon as possible, maybe over the Labor Day weekend. You know, take some time for yourself, but the chapter 1 homework, maybe do over the weekend after you turn in the chapter 0 homework. And don't forget, there's Alex for extra credit, although you do have until the end of the semester to take care of that. Was it December 14th or something? Right, December 14th. But most licenses are 6 weeks, right? So chapter 0 is the only one for extra credit. Any other general questions before we start the videos? And again, we'll have plenty of time at the end. Well, not plenty, but like 30 minutes, right? All right, so let's go ahead and start the videos. Feel free to keep chatting in the videos. We're recording, correct? We are recording, all right? By the way, on Thursday, I will record 1.3, but it depends on the students. The homework question session may or may not be recorded. I suspect, knowing the students, most of it would not be recorded, but it's up to the students. All right, anyway, let's go ahead and start with the videos, yes? All right. Oh, what's the deadline? Oh, okay, the deadline is Monday, December 14th. But remember, most of the Alex licenses are usually 6 weeks. Now, you are welcome to renew, and you are welcome to get longer term licenses like the 18-week license. But of course, that would cost more. So that depends on your budget. And it's extra credit. All right. Now, bear in mind, though, don't procrastinate. So, you know, if you want the extra credit, you know, try to be consistent. If you have like a long gap, then you're going to be reassessed and you might be taken back. Okay. Now, I do keep your best of. I get midnight reports that keep track of your best of so far. But let's say you fall back from, like one student fell back from 87% to 83%, then it's harder for you to beat the 87%. Although granted, if you make it to 87%, you're getting almost all the points anyway, right? That 25. So that student would get like what, like 24 points or something, or 23, 24. Well, would it be easy to finish in 6 weeks? It depends on you. Um, I mean, some of you already start off by knowing a lot, but be honest, right? So then Alex wraps around your brain. The whole point is for you to learn from the system. So be honest, don't use any aids when you take the initial screenings. And Alex will do a good system. It's an AI, artificial intelligence system that'll wrap around your brain. I'll tell you one thing though. The more honest you are with the assessment tests, the more honest you play with Alex, the less time it'll take. Because if you play games, then it may take you longer. All right. So make sure that you're honest and don't use any aids, any additional books or websites when doing the assessments. Okay. Any other questions before we start? Feel free to ask. There's not as much pressure today. I have some gap time at the end. Any other questions before we start chapter 1? Which again, I encourage you to do that homework as soon as possible, but I can understand if you want to wait till this upcoming weekend. Sure, do the chapter 0 homework first. That's the key priority. All right. So let's go ahead and start. Whoops, go to playlists. Hi, everyone. Let's start chapter 1 on general function theory. And we're going to start with section 1.1 with an introduction to functions. We'll go through the first part of it very quickly. A function is a special type of relation, which is a set of ordered pairs of the form input, comma, output. We can think of the inputs as x coordinates and the outputs as y coordinates. So for example, here's a relation, a set of ordered pairs. This relation maps, for example, the input 1 to the output 5, and so forth. Now a function has the special property that each input yields exactly one output. So we are not allowed to have the following happen. We are not allowed to have one input yielding 2 or more outputs. In other words, we cannot have a single x coordinate yielding 2 or more y coordinates. That is illegal for a function. It's not illegal for a relation in general, but it's illegal for a function. And by the way, something like this could be the graph of a relation, but it could not be the graph of a function. It violates the vertical line test. So a function is a special kind of relation where this is not allowed, an x yielding 2 or more y's. The domain of a function is the set of all input values. It's like the set of all first or x coordinates. The range of a function is the set of all the resulting outputs. It's the set of all the second or y coordinates. So we associate the domain with the set of x coordinates we pick up and the range with the resulting set of y coordinates we pick up in the usual setup. So let's go to this over here. The expression f of x is read as f of x or f at x. It does not mean f times x. So f of x represents a function value. That results from an input value x. Here, for f of x, x can be thought of as an input value or the argument of f. So x here represents the input or the argument for the function f. And we can think of a function as a kind of input-output machine, kind of like a calculator button on your calculator, like square root or x squared, the squaring function. So when we evaluate a function at its input, we're determining the resulting output. And we express it in simplified form. A function is defined, or it exists, only on its domain, only for those values of x in the domain of f. If x is not in the domain of f, then f of x is undefined, or does not exist. A function rule describes how a function assigns an output to an input. So something like this, f of x equals x squared. This tells us to take the input or argument x and square it to get the resulting output, the function value. Let's talk more about this squaring function. And this corresponds to the x squared button on your calculator. The domain is assumed to be the set of all real numbers. We can square any real number. So we're defining the function f by this rule, f of x equals x squared. The domain is assumed to be R. Now bear in mind that we could have just as easily defined this rule as f of u equals u squared. Please say f of u. Either way, f squares its input. I could say that f of grandma equals grandma squared. So if f is the squaring function, remember f is the function. If f is the squaring function, what is the value of f of negative 3? Evaluate this. Be careful. When you substitute in the negative 3 for x, remember to put grouping symbols. Always be prepared to put grouping symbols whenever you're substituting or plugging in. Don't forget to put grouping symbols around the negative 3 when you square it. The square of negative 3 is positive 9, not negative 9. If you write this without grouping symbols, this is negative 9, but this whole thing is wrong. The function value at negative 3 is positive 9. This is what the input-output machine does. If you put in negative 3 in your calculator as the input or argument, when you press the x squared button, which represents the squaring function, the output is positive 9. Now, we often classify functions based on the type of rule it corresponds to. For example, f is a polynomial function if we can define it as f of x equals a polynomial expression in x, like x squared plus 1, for example. And we can say similar things about rational functions and algebraic functions. So down here, for example, this is the defining rule for a polynomial function. This is the defining rule for a rational function, where we allow for fractions of polynomials. And this is a defining rule for an algebraic function in general, where we allow for things like rational exponents on x and square roots and cube roots and so forth of variable radicands. Remember, all polynomial functions are rational and all rational functions are algebraic. Next, various ways that we can represent functions, aside from a defining rule or formula. Okay, any questions before we go on? Any questions? Feel free to chat. Okay, any questions? All right. Hi, everyone. There are many ways to think of a function. Most students think of a function in terms of a defining formula or rule, like f of x equals x squared. But you can also think of an input-output machine, like a calculator button, or a verbal description. For example, this function squares its input to get the output. You can also think of a table of input-output pairs. In fact, you do this if you want to do point plotting for a graph. Again, a function is a kind of relation, which is a set of input-output ordered pairs. And you can graph these ordered pairs as part of an overall graph for a function. F of x is often replaced by y, and we can talk about this being the graph of the equation y equals x squared. We talked about functions as relations, which can be represented with an arrow diagram pointing from inputs to outputs. And we can also define functions in terms of computer algorithms or a series in calculus 2. Next, we'll talk more about the issue of domain. Okay, any questions before we go on? Any questions? These are short videos. I like doing it bit by bit here. All right, any questions?
Hi, everyone. Remember that the domain of a function is the set of all legal inputs to the function. I'll often abbreviate the domain of a function f by DOM of f. Now, if the domain is not given to you, we assume that the domain is the implied or mathematically natural domain of f. In particular, we're going to assume that it's the set of all real values of x for which the output is real. We have to keep it real. We have to keep it real. Now, sometimes in a word problem or a geometry problem, we might have other restrictions, like, for example, x has to be non-negative. But for the most part in this chapter, we're talking about the implied mathematically natural domain. So what are the two key sins? When you're dealing with algebraic functions, what are the two key no-nos? What are the two key things that lead to things that are not real, outputs that are not real? If we divide by what number, or if we take what kind of root of what kind of value. The implied domain of an algebraic function. The implied domain is a set of all real numbers, except those that lead to division by 0 or taking the even root of a negative value. For example, the square root of -1. I know we define this to be I later on, but again, we're keeping it real. For right now, this is not real. -1 is illegal for the square root function as an input. So for example, if f of x equals 1 over x, or x to the -1, then the implied domain is the set of all real numbers except 0. This is the set in set builder notation, or set difference notation, I should say. The set of all real numbers except 0. So 0 to the -1 is also illegal, because that's the equivalent of dividing by 0. It's like 1 over 0. Likewise, if g of x equals the square root of x, then the implied domain is the set of non-negative real numbers, corresponding to this interval form over here. Now bear in mind, 0 is included in the domain. The square root of 0 is 0, a perfectly good real number. People often forget that 0 is in the domain of the square root function. However, negative numbers like -1 are not, because the results will never be real. Next, let's talk about domains and ranges in general. Remember, the set of legal inputs is the domain, the set of resulting outputs is the range. So for example, for our squaring function, because we're talking about a polynomial function here, the domain of f is assumed to be all real numbers. So if the defining rule is given by a simple polynomial, the assumed domain is R, the set of all real numbers, or this in interval form. Now, what about the range? Now, sometimes the range is difficult to find until you graph the function, but for the squaring function, let's figure it out. So, for example, the square of 3 is 9. So 9 is in the range. But the square of what other number will also be 9? The square of -3 will also be 9. What's the square of 0? The square of 0 is 0. So notice that the squares of the various real numbers here will always yield non-negative results. Non-negative results. we never ever get negative results. We never get negative results. We only get non-negative results. And in fact, every non-negative number is in the range. For example, I claim that 7 is in the range. The square of what number gives me 7. He's a bit uglier, but it is the square root of 7. You can't argue with this. The square of root 7 is 7. So in fact, the range, by this kind of argument, the range is a set of all non-negative real numbers. Here's the range, the set of all y values in the reals such that y is non-negative. Since we associate range with y coordinates, I put y's here, but you can use any letters you want. You can use grandma and grandma. You can use any letters you want as long as you're consistent. Here is the set of non-negative reals in interval form, bracket 0, infinity, parenthesis. Next up, we'll consider the domains of various functions.
Okay, so we're going to do some cranking in the next video. Any questions about the theory thus far? Any questions about the theory? To keep it real, don't divide by 0. Don't take even roots of negative values. Any questions? Any questions? All right, keep chatting.
Hi, everyone. Let's find some domains. Again, we are looking for all real values of x for which the resulting output is real. Let f of x equal the square root of x minus 3. Find the domain of f, the implied domain of f. Well, when are we guaranteed a real output? When the radicand here, x minus 3, is what? What's that long word? When it's non-negative. It could be 0, it could be positive, it could be non-negative. So root x minus 3 is a real output if and only if the radicand, x minus 3, is non-negative. It could be positive or 0. We can add 3 to both sides of this inequality, and we get x is at least 3. X is greater than or equal to 3, which is the key. Notice here, these are weak inequalities. The bars here indicate that 3 itself is legal. 0 itself is legal for the radicand, x minus 3. The square root of 0 is 0. Don't forget that. That's legal. That's real. So the domain of f in set builder form is the set of all x in the reals such that this over here, the key, x is greater than or equal to 3. You can use a colon instead of the slash. Here's the graph. We include 3 and get all greater numbers. In interval form, again, 3 itself is legal. We have the bracket there, bracket 3, infinity, parenthesis. Typically, I'll ask for the interval form when I want the domain. Now that's the domain for f, where f of x equals root x minus 3. And it didn't matter if I used x or, for example, t. I could have said that the rule is given by f of t equals root t minus 3. And it wouldn't matter. The domain would still be the same set. I don't care if you put t's here, or x's here, or grandmas here, as long as you're consistent. It's the same set of numbers, all real numbers that are greater than or equal to 3. I don't care what letters you put here. Just be consistent. How would this domain be different? We just found the domain for root x minus 3. The domain for root x minus 3, the set of all real numbers greater than or equal to 3. How about f of x equals 1 over the square root of x minus 3? What happens to that radical is in the denominator? How would the domain be different? Well, when is this output real? The output is real if and only if the radicand, x minus 3, is what kind of value? Here, x minus 3 must be strictly positive. We have a strict inequality here. The radicand cannot be 0 because root 0 is 0, and we cannot divide by 0. Add 3 to both sides, and we get x is greater than 3. So the domain of f is a set of all real numbers that are strictly greater than 3. 3 itself is illegal. Notice the open hollow endpoint over here at the 3. In interval form, instead of a bracket, we have an open parenthesis. 3, comma, infinity, parenthesis. So it makes all the difference in the world if the radical is in the numerator or in the denominator. How about this? Let f of x equal the fourth root of 3 minus x. Find the domain of f. The hard part is actually not the fourth root. We may as well be dealing with a sixth root or a square root. The bottom line is that we have an even root. This may as well have been a square root. The thing that's tricky is the fact that the radicand is 3 minus x, not x minus 3. So when is this output real? When is this output real? The output is real if and only if the radicand is non-negative, greater than or equal to 0. It can't be 0 itself.
It can
Now,
be.
let's solve this inequality for x. And there are a couple of ways we can do this. This is a review of section 0.12 on inequalities. All right, method 1, we can subtract 3 from both sides. We get the opposite of x is greater than or equal to negative 3. And then we could multiply or divide both sides by negative 1. But remember that when you do that, what happens? The inequality symbol flips. And we get x is less than or equal to positive 3. We reverse the direction of the inequality symbol when we multiply or divide both sides by a negative number. Now, there's another way we could do this. Method 2, we could take 3 minus x is greater than or equal to 0. We could add x to both sides. Add x to the left, add x to the right. And then we get 3 is greater than or equal to x. And then we can switch sides. When we switch sides, again, we must reverse the direction of the inequality symbol. This time because we're switching sides about an inequality symbol. X is, again, less than or equal to 3. These inequalities lead to the same set. The domain of f is the set of all x's in their reals, such that x is less than or equal to 3. The graph includes 3 as a solid endpoint, and we extend to the left. We want lesser numbers, as well as the 3. The interval form follows a real number line, going from left to right. The left arrowhead here sort of corresponds to negative infinity, and we always put a parenthesis next to negative infinity. Negative infinity, comma, 3, bracket. We do include the 3 itself. This is a trick question. F of x equals the cube root of x minus 3. Find the domain of f. For what values of x will this be real?
I'll pause here for a moment. Any questions so far? Okay, because we've done a lot of algebra here. Any questions so far? What's the answer to this question? You shouldn't have to think that hard.
Well, all real numbers. The domain of f is all real numbers. In general, if you're taking the odd root, like the cube root, the fifth root, the seventh root of a polynomial, if you're taking the odd root of a polynomial, the domain is all real numbers, because we're taking the odd root of a polynomial. If f of x is the 11th root of a 20th degree polynomial, what's the implied domain? R, the set of all real numbers. Next up, all right, this is the big test. Find the domain of G. Next time.
Questions. Questions. So expressing the domain in set builder, graphically, interval form. Questions. These are algebraic functions. We're finding domains of algebraic functions. Any questions? Here's a big test right here. Whoa. Okay, can you explain the last one again? All right. So
Hi, everyone. Let's find some domain.
Okay, let me go to the notes. Okay. So I'll go ahead and go to the notes. All right. So, yeah. Okay. So the previous one before the monstrous guy. Oh, you mean this one? Oh, example 15. Oh, okay. So the idea here is we want to ask ourselves, first of all, when do we have a problem? When is there a problem? Well, this thing's a polynomial. If the radicand's a polynomial, we don't have a problem with a polynomial, right? All real numbers will work for x. If we're taking an odd root, again, we don't have a problem because you can take the cube root of -1, it's -1. The fifth root of -32 is -2. So an odd root of even a negative value is real. It's a negative number in that case. So polynomial, no problems. Taking the odd root of a polynomial, again, no problems. So we don't get a problem here. Domain is all reals. There are no restrictions. Right. Remember, it's like what Homer said to Marge, right? We like odd roots. We like odd roots because they don't cause problems. And we like polynomials because they don't cause problems. Now, if you have the cube root of something messed up, like tangent of x, okay, you got problems. But if you have like a cube root of any polynomial, or the 11th root, or like of a 20-degree polynomial, you're good, all reals. Well, now square roots are even roots, so you got to be careful there, right? As we saw before, with square roots and fourth roots, there are typically restrictions, right? Like the radicand is non-negative, okay? But odd roots of polynomials, great. Domain is all reals. There's not a problem. Unless you have a word problem or something, right? Any questions? Any questions? All right.
Eight. Again, we are looking for all real values of x
So
for which
I want to go to the end.
This is the big test. Find the domain of G. Next time.
If you can get this, you've really mastered it.
Hi, everyone. Let's be brave and find the domain of G here, where g of t equals the square root of 3t plus 9 all over 2t squared plus 20t. Remember, it's not always f of x. Here we have g of t. So when does this yield a real output? How do we keep it real? All right. G of t is real if and only if what two things are true. Well, notice here we have a square root on top. So what do we need to be true of the radicand, 3t plus 9? To keep it real, we only take the square root of what kind of value? Non-negative. And furthermore, the denominator, 2t squared plus 20t, cannot be what? In order to keep it real, the denominator, 2t squared plus 20t, cannot be 0. So g of t is real if and only if this is true and this is true. We can only take square roots of non-negative values, and we never divide by 0. Let's solve this inequality first. Let's solve 3t plus 9 is at least 0. We can subtract 9 from both sides. We get 3t is greater than or equal to -9. Remember, you do not flip the symbol if you just subtract. We divide by +3. Again, that does not flip the symbol. T is greater than or equal to -3. So we have this as a condition. G of t is real if and only if, basically, t is greater than or equal to -3. And, again, if this thing here is not 0. Okay. So
before we go on, you're okay with that, right? So for that inequality, then this inequality is equivalent to t has to be at least -3. But then we have to make sure the denominator is not 0, right? You're following?
We need 2t squared plus 20t to not be 0. Now here, I deal with inequations, but instead I'm going to go ahead and think in terms of equations. But remember, we want to avoid the following. We want to avoid a zero denominator. So we want to avoid 2t squared plus 20t equaling 0. This is what we want to avoid. At this point, it's a matter of solving the equation. Let's start by factoring out the GCF. The GCF is 2t over here, 2t. When you factor, you divide, we get this other factor here, t plus 10. So this factors as 2t times the quantity, t plus 10. And then we apply the zero factor property. So when does this product equal 0? If 2 equals 0, or t equals 0, I could probably type these out. If 2 equals 0, or t equals 0, or t plus 10 equals 0. Well, 2 never equals 0. I can zap that. That's a dead end. Okay. Or t equals 0, or subtract 10 from both sides. T equals negative 10. So is that the domain? T equals 0, t equals negative 10? No, 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 no. These are the bad guys. These are the bad guys. We have to avoid t equals 0 or t equals negative 10. Okay, so what's the negation of this? The negation. The negation is t cannot be 0 and t cannot be negative 10. Of course, you're wondering, why are we going from or to and? That's a logical rule called De Morgan's laws. It's a set of rules. Basically, De Morgan's laws say that the negation of an or expression is an and expression, and vice versa. So for example, what does it mean to not be an American? Well, what does it mean to be an American? It means that you're an Alabaman, or an Alaskan, or an Arizonan, or so forth. But wait a minute. That means that you're not an Alabaman, and you're, this is in red. You're not an You're not an Alabaman, and you're not an Alaskan, and you're not an Arizonan, and so forth. You're not this, and you're not that, and you're not that, and you're not that. The negation of an or expression is an and expression. You're not an Alabaman, and not an Alaskan, and not an Arizona, etc. So here, the negation of an or expression is an and expression, together with what we had up here. So let's collect all of our restrictions. T has to be greater than or equal to negative 3, and t cannot be 0, and t cannot be negative 10. But now wait a minute, this might be overkill. This might be overkill, because take a look here. Consider the real number line. All right, it's a t number line. From this top here, we want negative 3 for now, and we want all greater values. That's based on this inequality over here. But t cannot be 0. So that means we have a hole at 0, we want to skip over the 0, and a whole at -10, but wait a minute. -10, that's already out. That's already out. That's not in this purple shaded region anyway, right? -10 is not at least -3. So -10 was dead meat anyway. I'll put it this way over here. -10 was dead meat anyway, because -10 is not greater than or equal to -3. So this is really superfluous. It's redundant. We don't need this if we already have that. So really, we just need these two conditions. In step builder form, the set of all t's in the reals such that t is greater than or equal to -3 and t is not 0. On the graph, we start with -3. That's a solid endpoint. We want greater values as well, but we skip over the 0. We don't want the 0, so we put a pothole there. We skip over the 0, and we get this right wing over here. What's this in interval form? I'll give you 10 seconds. It helps a lot to do the graph before you write down the interval form. Well, we include the -3, so bracket, -3, comma, 0, parenthesis, we skip over the 0, union, parenthesis, 0, comma, infinity, parenthesis. We skip over the 0, we have parentheses around the zeros. All right, so this is the domain of this function g, the set of all real values for t for which this output is real, and only those values.
Okay, so let's pause here. In fact, I'll go back a little bit. All right, so any questions? This was kind of the monster of the day, right? So let me go over it again. Okay, so again, to find the domain, I need to make sure that, I need to make sure that the radicand here is non-negative. Ultimately, that means that t has to be greater than or equal to -3 when I sort of simplify, when I solve for t here. And I need this thing to be non-zero, which means that I have to exclude both the 0 and the -10, but this is superfluous because this is taken care by that anyway. I need this. So I really have two basic restrictions. T has to be at least -3, and t is not 0. Yes, t cannot be -10, but I knew that all the way back here anyway. All right. So I just needed these two key restrictions here. All right. Any questions about that? If you got that, then you're in very good shape. Any questions?
Parenthesis. We skip over the 0, we have parentheses around the zeros. All right, so this is the domain of this function g, the set of all real values for t for which this output is real, and only those values. Next up, how you evaluate functions. Hi, everyone. How do we evaluate a function? How do we find a function output? So let's take this g of t rule from the previous example, and let's consider the values of g of 1, g of pi, g of 0, and g of -4. First of all, some of these will be real and defined outputs, and some of these will be non-real, and therefore undefined as outputs. Which ones? I'll give you a hint. Here's the domain that we obtained in the previous example. Is 1 in the domain of g? Well, 1's in this right interval, so yes, g of 1 is a real output. 1 is in the domain. What about g of pi? Well, yes, pi, again, is in the right interval here, so g of pi will be defined and real. But what about g of 0? 0 is not in the domain. We skip over the 0, so g of 0 is undefined. What about -4? G of -4. Well, -4 is not in the domain. It's to the left of -3. So g of -4 will also be non-real and undefined. So of these four, g of 0 will be undefined, and g of -4 will be undefined. However, the others will be real and defined. We're going to get real outputs for these two. Now, if I ask you to evaluate g of 1 or g of pi, you may not have to find the domain first. It's often the first question we ask about a function, what's its domain? But bottom line is, if I give you a rule for g of t, and I ask you what g of 1 and g of pi are, usually what you would do is you would just plug in t equals 1 and see what happens. You'd plug in t equals pi and see what happens. For that matter, you could plug in 0 and -4, and again, you would see what happens. So for example, if you plug in 1 for t, we find that g of 1 simplifies to √3/11, which is a real number. It's kind of ugly looking, but it's a real number. 1 is clearly in the domain. What about g of pi? We'll plug in pi for t over here. The result might be kind of ugly looking, but it's a real value. So pi is in the domain. We get a real output. But wait a minute. What if you try to plug in 0 for t? We'll see what happens. And it turns out you get a 0 denominator, which means right there you know, hey, g of 0 is not real, it's undefined. Or you could have found the domain at the outset, and you would realize that 0 is not the domain. Likewise, if you try to plug in -4 for t, the problem here is that we try to take the square root of a negative number, which is a no-no. Again, the result is not real, it's undefined as a real value. Or again, we could have found the domain, as we did here, and we observe that -4 is not in here. But if you're given g of t equals blah, 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 and you're asked to evaluate, instead of finding the domain explicitly at the outset, although theoretically we should, still, to evaluate these things, you plug in these values for t, and you see what happens. Do you have a problem with division by 0, or the even root of a negative number, or not? Again, 1 and pi are in the domain of g, so these values are defined as real numbers. 0 and -4 are not in the domain of g, so these are undefined as real numbers. Next up, a more complicated evaluation.
Okay, questions before we go on? Any questions? Okay, good chatting. I like this interaction. Good chatting. Okay, any questions?
I have a question.
Sure.
So you just said that if we were given like a list of questions where it says evaluate this number, evaluate that number, we would normally just plug in those numbers to the equation and see whether or not we get an undefined solution, correct?
You're right, because, you know, sometimes finding the domain, as we saw for this guy, finding the domain can be a pain. Now, often I'll ask, what is the domain, okay? And then it should be clear which ones are defined and which are not. But if you're not required to find the domain, then just go ahead and plug in and see what happens. Granted, you'll go ahead.
Would it be acceptable, though, if we were to just find the domain and then specify for each of those that whether it is or is not within that domain?
Well, then you would figure out that g of 0 and g of -4 are undefined, but you would not yet know the values of g of 1 and g of pi.
Okay. Okay.
Right. But at least you know they're real. They're real, and you'd be getting a real result.
Okay, cool. Thank you.
Yeah. Bear in mind, when you go to calculus, your calculus professor will just assume, oh, of course you try to take the domain, because that's like the first question, theoretically, you're supposed to ask about a function. What's its domain? So your calculus professor might say, oh, of course you thought about the domain. Really? I did? Yeah. All right. Any questions? So yeah, theoretically, you're supposed to consider the domain, but here it's kind of a pain. So I'm being practical. Questions? Questions?
Sorry, just to make sure. So
Sure.
-4 doesn't work because it can be in the square root. Like we can't.
So a couple of issues. First of all, if you determine the domain first off, -4 is not in the domain, right? It's off to the left here. It's not in the domain. But even if you didn't figure out the domain first, plug it in. Plug in -4 for t, okay, into this expression. And if you try to do that, that's over here. Oh, what's the problem? Up here, you're trying to take the square root of a negative number. If you ever try to do that in this evaluation process, you're dead. As far as the real output goes, you're dead. Right there, undefined is a real value.
Okay. Okay, sounds good.
Mm-hmm. And by the way, that's true. Even if you get something like this, even if you get like the square root of -3 over itself, some students might say, well, isn't that basically 1? No, at any stage, if you see stuff like this, you're dead. Okay, we're very resistant to negative radicands. Questions? Questions? It's good to have this interaction. Questions? All right. Feel free to refer back. That's okay.
Hi, everyone. Let's do a more complicated evaluation, but something that we'll see in Chapter 1 at the end, and also in calculus. Let f of x be 3x squared minus 2x plus 5. Given this, evaluate f of x plus h. What happens if the argument is more complicated? X plus h. And the key...
Whoa, sorry. I'm
Given this, evaluate f of x plus h. What happens if the argument is more complicated? X plus h. And the key word to remember here is the S word, substitution. Back here, when we worked out g of 1, g of pi, we substituted 1 for t. We substituted pi for t. These are substitutions. Likewise here, we're going to substitute x plus h for x. Remember, it's a substitution. It's not just ya plus h. That's a very common error. You don't just do that. That's wishful thinking. Or as the late Carrie Fisher would say, wishful drinking. When you see something like this, think substitution. You're evaluating a function. And often f of x plus h does not break up like this or this, and that's often not the case. All right, think substitution. So if f of x is this, 3x squared minus 2x plus 5, how do we even express f of x plus h? Well, again, substitution. Every time you see an x, you replace it, you substitute it with the quantity x plus h in grouping symbols. Here we have an x. Here you put parentheses, x plus h. The plus 5 just carries over. Substitution. Every time you see an x, you substitute it with the quantity x plus h. To square a binomial, it's not just x squared plus h squared. It's x squared plus 2xh plus h squared, and these are all multiplied by 3. Here I distributed, we get minus 2x and minus 2h, and then the plus 5. Finally, distribute the 3. So we get 3x squared plus 6xh plus 3h squared. And then minus 2x minus 2h, that all carries over, and the plus 5. So once you get to here, you're set. If you remember the 2xh term when you square the binomial. Okay, I'll put these in purple for extra stress. If you know to substitute and you remember not to miss the middle term, the 2xh, then you should be set. You may think this is a bit of a mess. Bear in mind that at the end of chapter 1, we're going to make things a lot cleaner. When we talk about difference quotients and then derivatives. Okay, finally, let's talk about some applications of functions. You see them all over the place. Physics, the position or height of a coin as a function of the amount of time since the coin was dropped from the top of a building. The temperature of a room in Fahrenheit degrees as a function of the temperature in Celsius degrees. Also kind of physics. Over here, economics. The profit that a company makes as a function of the number of units produced and sold by a company. Later on, the comedian Rodney Dangerfield will describe widgets. So we see functions all over the place. Physics, economics, all over the place. F of x, P of x, G of t, and so forth. Next time, let's graph functions, section 1.2.
Okay, that's it for section 1.1. Any questions as we look back? Right, remember, the odd roots are much more liberal. So we can take the cube root, the fifth root, the seventh root of a negative number, we get a negative number. So basically, the odd root of something good is good. Whereas the square root or the fourth root of something good might not be good. So remember, odd roots are more liberal. Odd roots allow for negative radicands, and we're okay. Questions? Questions? Okay, lots of good chat. Ready for section 1.2? Actually, you know what, folks? Since we have a bit of gap at the end, we can take a break now. It's 8:01. Let's take a break now, and I'll see you at 8:12. All right? So let's take a break now, and then we'll start 1.2. I'll take questions at the end. All right. Okay, I'm starting the recording. Any questions before we go on? We're going to start 1.2 on graphs. Any questions? All right. So let's get started.
Hi, everyone. In section 1.2, we're going to graph functions using our usual setup. So we're going to graph a function f in the xy plane, where y is a function of x. So we have the equation y equals f of x that we want to graph. This graph will consist of all points of the form x comma f of x, where x is in the domain of f. So we're going to graph all points corresponding to these ordered pairs, where we have these values in the domain of f and these function values as their corresponding y coordinates. That's a key thing to remember. In the usual setup, function values are y coordinates. Function values are y coordinates. The outputs are y coordinates for points on the graph. Basically, x corresponds to domain, y corresponds to range. X is the inputs, y is the outputs. X is the independent variable because it's the input variable, is what we plug into a function. Y is the dependent variable, is the output variable, because the function value typically depends on what the input value is. What your calculator spits out usually depends on what you enter into your calculator. The calculator button would be the function. Now, by the way, in section 1.8, we're going to talk about x as a function of y. That's later. Also later, in sections 1.3 and 1.4, we're going to discuss basic graphs and how to manipulate them. Well, let's say for now, I give you a function, y is a function of x, and you have no idea how to graph it. How can you do it brute force from scratch? We can use point plotting. It's a last resort, but it's there. So first of all, you need to consider the domain of the function f, and you're going to choose several values, several x values in this domain. For each of these x values, you're going to find the corresponding function value. Function values are what? They're going to be y coordinates. You're going to graph the corresponding ordered pairs, x comma y, x comma the function value. You're going to graph these points in the xy plane. So you're going to graph the points from your table, and then you're going to basically connect the dots, interpolate, and then extrapolate, go beyond as seems reasonable. So there is some guesswork here. Okay, as an example, we're going to graph the square root function, where f of x equals the principal square root of x. In other words, we're going to graph y equals root x. In the usual setup, we can replace f of x with y. Function values are y coordinates. First off, it would help to consider the what of the function. This is often the first question we ask about a function. What is its domain? What is its domain? Well, what are the legal values for x? What guarantees that we will keep this real? If and only if x is, again, non-negative. X must be non-negative. The domain of f consists of the set of all non-negative real numbers. Bracket, 0, comma, infinity, parenthesis. Remember, the square root of 0 is 0. That's legal. So, for example, positive 9, whoops. For example, positive 9 is in the domain, but negative 9 is not. Positive 9 is in the domain, negative 9 is not. So when you construct a table, you might want to plug in x equals 9, but you would not plug in x equals negative 9. You know that you're not going to have a point on the graph where the x coordinate is negative 9 or any real number, or any non-negative real number for that matter, which means you're not going to have any piece of graph over here for negative values of x to the left of the y-axis.
So to clarify, we're bad if we have negative numbers, right? Negative numbers, you have no points here with negative values for x, right?
Good sample values of x to plug in because these are perfect squares. The square root of 0 is 0, so 0, comma 0 is on the graph. Over here, the square root of 9 is 3. The function value is 3, so that's our y-coordinate. We want the point where x equals 9 and y equals 3. That's this point over here. In principle, we want to graph all points of this form, x comma f of x, where x is in the domain of f. We do definitely want this point 0, 0 here because that's an endpoint. We want to clearly indicate all endpoints on the graph. Notice that 0 is the endpoint of this domain here. We're going to want to plug in x equals 0 to find out the endpoint for this graph. You must indicate endpoints. Over here, we assume that the graph extends on and on. Some people put an arrow, but even without the arrow, if the graph extends to the edge of the figure, we assume it goes on and on as expected. So we point plot these 4 sample points, we interpolate, and we extrapolate. We go beyond. Now you can graph these things on Desmos, but bear in mind that even Desmos might mess up sometimes, so it helps to know what's going on. Often, nothing beats the human mind. Graphing utilities might get confused. All right, next up, we're going to talk about how to tell when a graph represents y as a function of x.
Any questions so far? Any little details? Any questions? All right.
Hi, everyone. How do we know that this graph represents y as a function of x? Here's Desmos. Y equals, you could put SQRT for square root and put the x in there. Or y equals, you could go to the keyboard in the lower left, the keypad. Here's square root, and put the x that way. The down arrow to close it. But how do we know that this graph, I'll zoom out, how do we know that this graph represents y as a function of x? It's because it passes the vertical line test, the VLT, not BLT, VLT. So what does the vertical line test say? A graph or a curve in the XY plane passes the vertical line test, the VLT, if and only if there is no vertical line that intersects the graph more than once. So if we do not get something like this, we're not allowed to have a situation where one x coordinate yields 2 points with 2 different y coordinates. We're not allowed to have one x value from the domain yield 2 different y values. That's a no-no. That's a no-no. Because if this were to happen, that's like if you punch in 3 into a calculator, press a button, and the calculator says, oh, I don't know, the answer could be 7, it could be negative pi. the function value could be 14 or 42. I don't know. I'm going to go get a VLT. Then that would not be a function. We would not have y as a function of x. If you have one x value in the domain, you're going to get one y value in the range, and that's it. So take a look at this square root graph. When we look at these various vertical lines, okay, this vertical line hits no points. That's okay. You're not allowed to take the square root of a negative number for now. If you try to take the square root of -1, then your calculator will say error. That just means that these values, like -1, are not in the domain of the function. That's okay. So 0 points, 0 points, 0 points. These are values that are not in the domain of f. But then 1 point, 1 point, 1 point, 1 point. For each of these x values, here in the non-negative values of x, we do get exactly one y value. The graph does pass the VLT. This graph does represent y as a function of x. Now, here we have an equation that does not represent y as a function of x. X squared plus y squared equals 9. And try to remember, what was the graph of x squared plus y squared equals 9? Remember that? X squared plus y squared equals 9. It's a circle of radius 3, not 9, radius 3, starting at the origin. Does this graph pass the VLT? Absolutely not. For example, x equals 2 cuts the graph in 2 points. X equals 0 cuts the graph in 2 points, and so forth. So if you plug in x equals 2, okay, it turns out that that both y equals root 5 and y equals -5 will work in conjunction with x equals 2 to solve this. More easily, if you plug in x equals 0, then y equals +3 and y equals -3 will correspond to points on the graph. For example, 0, 3 lies on the graph, 0, -3 lies on the graph. But then that means that we're failing the vertical line test, because we see at least one vertical line that cuts the graph in more than 1 point. Again, this is like saying if we input 0, we're getting outputs of 3 and -3. And a function is not allowed to do that. Another way to see this is to take the equation x squared plus y squared equals 9 and try to solve this for y, to try to get an explicit form, y is a function of x. Well, try it, and this is very instructive. Let's solve x squared plus y squared equals 9 for y. All right, let's do this. So first off, let's isolate the y squared term. How would we do that? We would do what with the x squared? We would subtract it from both sides. So we take x squared plus y squared equals 9, and we subtract x squared from both sides. So on the left side, we're left with the y squared term. On the right side, we have 9 minus x squared. Now we're going to apply the square root method. I'll give you a hint. Let's say that we had a squared equals 7. If a squared equals 7, what could a itself be? Don't just say the square root of 7. It could be plus or minus the square root of 7. I'll put this in red to really emphasize that. It's plus or minus the square root of 7. So likewise, what's equivalent to y squared equals 9 minus x squared? It's y equals plus or minus the square root of 9 minus x squared. But then it should be evident that if you plug in values like x equals 0 or x equals 2, you're going to get two different values for y. For example, if you plug in x equals 0, you're going to get both +3 and -3 as values for y. So this is another way of seeing that we do not have y as a function of x, at least not directly, not explicitly. But hold on now. When you look at this circle, isn't it true that there are pieces of this circle that pass the vertical line test? That leads to the idea of implicit functions. So even though, as it stands, this circle does not represent y as a function of x, this does lead to infinitely many implicit functions that correspond to pieces of the graph that do. So for example, remember that x squared plus y squared equals 9 is equivalent to this over here. How would I get the top half of the circle? What would you enter into Desmos to get the top half of that circle? You would take y equals straight up root 9 minus x squared. You delete the plus minus. Let's do that. So on Desmos, let's have it graph y equals the square root of 9 minus x, shift 6 for the exponent, 2. Look at that. We have the upper half of that circle. And this graph does pass the VLT. That indicates that y equals root 9 minus x squared does express y explicitly as a function of x. Well, likewise, how do we get the bottom half? We take y equals the opposite. We take that sort of minus sign there. We take y equals the opposite of root 9 minus x squared. Let's do that. Y equals the opposite of root 9 minus x squared. Just to be safe, I put parentheses. And we get in black the bottom half of the circle. So in principle, you could get the whole circle by combining the purple graph and the black graph. Both of these are implicit functions from the original equation up here. The idea of implicit functions does come up in calculus because we might be interested in slopes of tangent lines, rates of change. Okay, so we get the upper half of this circle from this equation. Remember this form because we'll see it in 1.3. And also we graph this equation to get the bottom half of the circle. We get the endpoints as well. Next, given a graph, estimate domain, range, and function values from a good graph.
Okay, so that was important, going over circles. All right, that's section 1.2. Any questions about that? So remember these forms. Yeah. Okay, so guys like these, we're going to see again. Any questions? Any questions? All right.
Hi, everyone. Let's say we have a graph where y represents a function of x. Well, let's estimate the domain, range, and function values from such a graph. Remember that the domain of f in the usual setup is the set of all x coordinates of points we pick up on the graph. The range of the function is the set of all y coordinates of the points we pick up on the graph. If you input x coordinates from the domain, you press that calculator button F, the outputs are function values, y coordinates in the range. So you can think of it this way. You can think of, in the xy plane, you can think of taking a graph, projecting it onto the x-axis, smushing it onto the x-axis to get the domain, and then smushing the graph, projecting the graph onto the y-axis to get the range. Take this graph over here. Estimate the domain and the range of this graph. Assume that the graph extends as expected over here and over here beyond the window. Also, estimate f of 1 for me. And by the way, I say estimate because who knows? Maybe the y coordinate here is 0.99. Well, no, it does turn out to be 1. We have a y-intercept at 0, 1. But I say estimate because, well, not everything's integer. This is 1. All right. That's the graph of y equals x squared plus 1, by the way. To estimate the domain, ask yourself, what are the x coordinates we pick up on the graph? Well, assuming the graph extends as expected, we pick up all real numbers. But that should be expected because we have here a polynomial function, and that is the implied domain for any polynomial function. The domain we expect to be R, the set of all real numbers, this over here. Now for the range, we project onto the y-axis. 1 is the least real number we get in the range, and we get all higher numbers. So it looks like the range of f starts at 1, that's bracket 1, comma, infinity, parenthesis. So we've estimated the domain and range based on this graph. And let's estimate f of 1. Well, remember, function values are y-coordinates. So when x equals 1, what's the corresponding y-coordinate? This is the point 1, comma 2. Okay, on Desmos, here's the point 1, comma 2. It's on the graph. When x is 1, y has to be 2 on the graph. We estimate f of 1 equals 2. Now, in section 1.1, we talked about finding the domain of a function given its rule. Bear in mind that the range question can sometimes be a much harder question. Sometimes you cannot find the range of a function until you get the graph. Then you can find the range. Ranges are often harder to find than the domain. Next up, notice this graph does not have any x-intercepts. Why is that? Because this function value is never 0. Y is never 0 on this graph. How do we find x-intercepts and therefore zeros or roots for the function? Next time.
Okay, any questions before we go on? We're in bits and pieces here, in part because I kept being afraid of making a mistake. So I have these small videos. Any questions? Any questions? All right.
Hi, everyone. How do you find the x-intercepts on the graph of y equals f of x? Well, in general, how do you find x-intercepts in the xy plane? You set y equal to 0. You set y equal to 0. You set the function rule equal to 0. And you find the real solutions of this equation. The real solutions of this equation are the real zeros or roots of f. Bear in mind that the number 0 itself may or may not be a 0. So the term 0 might be misleading. But then again, the term root can also be misleading as well. Bottom line, we want the real solutions for y, or f of x, equal to 0. Now, to find the y-intercept, that's usually easier. To find a y-intercept, we plug x equals 0. We plug in x equals 0, which means that we're evaluating f of 0. And we identify the corresponding point, 0, comma, f of 0. If 0 is not in the domain, then there is no y-intercept. Example. Basically, find the x-intercepts of the graph of y equals f of x, where f of x is x squared minus 9. I basically want to consider the graph of y equals x squared minus 9. So how do we find x-intercepts? We set y, or this function rule, equal to 0. We're solving an equation. You set x squared minus 9 equals 0, solve the equation. There's no x term, so we can add 9 to both sides and use the square root method. X squared equals 9, and then x equals plus or minus, don't forget the plus or minus, 3. So 3 and negative 3 are the real zeros or roots of this function. Therefore, the x-intercepts are at the points 3, 0 and negative 3, 0. Remember that we normally write x-intercepts as ordered pairs. And again, to find x-intercepts, we have to solve an equation. We solve the equation y, or f of x, equal to 0. So here's the graph of y equals x squared minus 9. If we zoom in a bit, we can see that the x-intercepts are going to be at negative 3, 0, and at 3, 0. Those are our x-intercepts, where the graph hits the x-axis. Now, where's the y-intercept? Well, that's usually easier because to find a y-intercept, that involves evaluating at 0. So you're basically finding f of 0. When you plug in 0 for x, here, you get y equals -9. So that means that the point 0, -9 is the y-intercept. So once again, x-intercepts can tend to be harder to find because you have to solve an equation. Y-intercepts tend to be easier to find because that just involves basically evaluating at 0. Assuming that these intercepts exist. You might have graphs where neither will exist. But for here, we have two x-intercepts. Our y-intercept will be at the point 0, -9. All right. Here's the graph once again. X-intercepts here in black, y-intercept in red here. Let's say we have radicals involved. So here's the idea. The root, in general, the nth root of g of x equals 0 if and only if g of x, the radicand itself, is 0. So basically, to find the zeros of a radical is quite easy. You can just remove the radical and consider the zeros of the radicand. The zeros of a radical are just the zeros of the radicand. So for example, if I ask you to find the x-intercepts for y equals root x squared minus 9, well, really, it boils down to finding the real zeros of just the radicand, x squared minus 9. And we've done that. We already found that the real zeros were 3 and -3, so we get the same x-intercepts as before. Although the graph we're talking about, y equals the square root of x squared minus 9, looks a bit different. Notice the graph disappears in the middle here. Why is that? Why does the graph disappear here? Because the values of x in here are not in the what of the function. They're not in the domain of the function. The values of x in here, like 0, they're going to make the radicand negative, like -9. And that's going to be illegal. We want to keep things real. Look at the impact that the square root operator has on x squared minus 9. So notice here that although we do get a flattening out here and out here, as you might expect, actually we get a steepening as we approach the two x-intercepts. And the black graph, the actual square root graph, the black graph shares the same x-intercepts as the red graph. So again, the point I was making before, the x-intercepts don't change whether you apply the square root here or not. The domain could change here. These values are around 0 or no longer in the domain. But the x-intercepts stay the same, whether there's a square root there or not. What if we have a fraction? Well, in general, when does a fraction equal 0? When which part equals 0? A fraction is equal to 0 when the top part is equal to 0, but the bottom part is not. Otherwise, you have a domain problem. Remember, if you're dividing by 0, then that's a domain problem, and this thing is undefined. 0 over 0 is undefined. 0 over any other real number is 0. Okay, so how do we find the x-intercepts in this case, where f of x equals a numerator over a denominator? To find the zeros of a fraction, you want to find the zeros of the numerator, but they have to be in the domain of the overall thing. So we want to find, so where are the zeros of f? They're the zeros of the numerator, but they have to stay in the domain of f. In particular, they cannot be zeros of the denominator. So in a typical setup, you want to find values for x that will make the top 0, but not the bottom. Although there could be other domain issues, like if you're dealing with tangent of x or something. But for a typical algebraic function, you get zeros if the top is 0 and the bottom is not. All right, so let's find the zeros of f, where f of x equals the fraction x squared minus 9 over x plus 7. So when does this equal 0? We're finding x-intercepts. When does this y guy equal 0? When the top is 0 and the bottom is not. When the top is 0 and the bottom is not. So we want to know when x squared minus 9 equals 0. Well, we've answered this question several times before. This fraction equals 0 if and only if the top, x squared minus 9 equals 0. And by the way, when the bottom is not. And the bottom is only 0 when x is negative 7. So if we get negative 7, we better reject it. But when you solve x squared minus 9 equals 0, we know once again that the only real solutions are 3 and negative 3. Negative 7 is not in the mix. If it were, we'd reject them. And once again, we have the same x-intercepts as before, at 3, 0 and negative 3, 0. Here's the graph. So parentheses, use parentheses, x squared minus 9 over parentheses x plus 7. This is f of x. All right. And notice, once again, we have the same x-intercepts. We have the same x-intercepts at 3, 0 and at negative, at 3, 0 over here, and at negative 3, 0 over here. By the way, these points in gray, we have the y-intercept here, and we have a minimum point over here. Interesting. To find the y-intercept, plug in x equals 0, you get negative 9/7. So the y-coordinate here is about negative 9/7. If you don't believe me, 0, negative 9/7, boom, the y-intercept. There you go, y-intercept. That was easier. All right. This problem is surprisingly harder. If f of x equals the fraction x squared minus 9 over x minus 3, again, let's find the x-intercepts. I basically want to find the real zeros of this fraction over here. Once again, I need to make the top 0, but not the bottom. For an easy rational expression like this, it's as straightforward as that. We want to make the top 0, but not the bottom. All right. Well, here's the deal. When you solve x squared minus 9 equals 0, you get two tentative solutions. Okay, you get two tentative solutions, 3 and negative 3. But wait a minute, 3 makes the denominator 0. So you can't have that. 3 makes the denominator 0, you can't have that. Negative 3 is the only real solution to this equals 0. Negative 3 is the only real 0 for this. So negative 3, 0 is the only x-intercept. Here's the graph. I'll do a new thing here. Parentheses, x squared minus 9 all over x minus 3. Oh, look at this. Look at this. We get a line. Really, there should be a hole over here at 3, 6. So Desmos is being a little naughty. We'll talk about this in chapter 2. But this is really going to, so the graph of y equals this is going to be a slanted line where there should be a hole at 3, 6. Right. But we really basically get a line. Think about that. Think about why that is. We only have one x-intercept at negative 3, 0. That's our only x-intercept. And once again, why is that? Let's trace the logic. When does this thing equal 0? Okay, when does f of x equal 0? When, not 6, 0. It's 0 if and only if x squared minus 9 equals 0 and x minus 3 is not 0. X minus 3 is not 0. I'll put that in green. X minus 3 is not 0. Or more simply, x is not 3. x cannot be 3. So from the purple here, x squared minus 9 equals 0, we get, oh, so I'll put a parenthesis here. X could be 3, or x could be negative 3, as we've seen a million times before. These are the real zeros for x squared minus 9. But wait, and, hey, wait a minute, there's a restriction here. X cannot be 3. It's a restriction that's relevant. The restriction up here that x couldn't be negative 7, that turned out not to be relevant in the end. Here, oh, this is relevant. This tells us that we have to reject x equals 3. We have to reject x equals 3, like Taylor Swift rejects a boyfriend. All right. We're left with x equals negative 3. All right. So negative 3 is the only real zero for this guy here, the fraction. All right. So we only have one x-intercept, negative 3, comma 0. All right. Next up, this is our monster for the day. Find the t-intercepts for the graph of y equals this thing. The key thing is find the real zeros or roots for this. We'll do that next time.
Okay, so we'll pause here. Any questions? We've talked about zeros and x-intercepts. For radicals, just remove the radical. For fractions, basically it's when the top is 0 and the bottom isn't. There are some more exotic examples, but for a basic rational, certainly, and for almost all algebraic functions, you're good thinking that way. Any questions? We're going to hit our monster for today.
Hi, everyone. Let's test our mastery. Let's find the t-intercepts now, the t-intercepts of y equals this thing over here. In other words, we want to find the real zeros or roots of g, where g of t equals this, the fraction, the square root of 3t squared minus t minus 4 all over t minus 3. To find the t-intercepts, we need to set y, this function rule, equal to 0. So when does this fraction equal 0? When the top is 0 and the bottom is not. In particular, 3 is excluded from the domain because it yields a 0 denominator. Now, you might be asking, well, wait a minute. What if the radicand here is negative? Aren't I in trouble? Yeah, but here's the thing. We're looking for cases where t is going to lead to a 0 value for the radicand. In order for the top to be 0, we need the radicand here to be 0. So we're only going to care about values of t that are going to make this radicand 0, and therefore the radical equal to 0 anyway. So don't worry about the values for t that'll make this radicand negative, because we're not looking for those values of t anyway. Now, actually, if we had a square root or fourth root down here, we might be a bit more worried. But no, the radical's on top. And again, even though the domain of g excludes values of t that yield negative values for this radicand, we don't care about those values anyway. We only care about the values of t that make the radicand 0 anyway. All right, bottom line. We care about the real values of t that will make the top equal to 0, but not the bottom. All right. So this fraction equals 0 if and only if the top, the numerator, equals 0, and the bottom does not equal 0. So the condition that t minus 3 cannot equal 0, that's equivalent to t not being equal to 3. We can add 3 to both sides of that equation. So if we get 3 as a tentative solution here, we better reject it. Let's see what happens. First of all, the square root of something equals 0 if and only if that something, that radicand, equals 0. Piece of cake. We can just remove the radical. Now, to find the real zeros here, it turns out that old school factoring will work. if you work out the discriminant, it'll be a perfect square. Old school factoring says we get 3t minus 4 and t plus 1. It might take some time for you to figure that out, but this is the old school factoring of this cutie. That product equals 0. Remember, t cannot be 3. We use the zero factor property, which tells us that this product will equal 0.
Let me go to, okay.
0 if and only if at least one of these factors equals 0. So we set 3t minus 4 equal to 0, solve that for t. We set t plus 1 equal to 0, solve that for t, and we get 4/3 and also -1 as our real zeros for this quadratic, and therefore of this guy all the way up here. So the zeros of G, the real zeros of G, are 4/3 and -1. And they correspond to the t-intercepts. Remember, these are going to be t-intercepts. They're going to correspond to the t-intercepts, 4/3, 0. T takes the place of x here. 4/3, 0, and -1, 0. If you don't believe me, let's use Desmos to get a graph of this. And we can use t. Hi, everyone. So let's graph y. Y equals the square root of 3t squared, right arrow, minus t minus 4, right arrow, all over t minus 3. Okay. And where are the t-intercepts? We're claiming that the t-intercepts are at 4/3, 0 and -1, 0. 4/3, 0. Yes, in green. And -1, 0. Yes, in purple. Okay. And in calculus, you'll be able to figure out what the graph looks like. It's like these 3 electrical strings out here. But even in this class, we were able to talk about domain and vertical asymptotes later in this class. That's the graph. And actually, the t-intercepts were the same ultimately as for y equals this guy, 3t squared minus t minus 4. Y equals 3t squared minus t minus 4, right? It's an easy parabola, and it had the same t-intercepts. All right, so we simplify the problem. Also, another way to get the t-intercepts from this quadratic, well, before we factored, you could have also used the quadratic formula, the QF. A equals 3, B equals -1, be careful with signs. C equals -4, again, be careful with signs. Apply the quadratic formula. The discriminant here, b squared minus 4ac, is 49. That's a nice perfect square. That tells us that old school factoring did help us here. We could factor over the integers because the discriminant was a nice perfect square. That means we could factor this cutie old school. We end up with, taking both the plus and minus cases, a 4/3 and -1. I hope so, because we need the same t-intercepts as before. Okay, next up, let's talk about some properties of graphs.
And I just realized there's a song I want to play for you folks. Thanks. Oh, I almost forgot that. All right, let me record.
Hi, everyone. If you do a good job of drawing a graph, you should be able to determine the intervals of increase and the intervals of decrease for the function. Here's the graph of y equals this cubic. We say that the function increases on this interval over here, decreases on this interval over here, and goes back to increasing on this interval over here. We say that this here is an interval of increase because if you take any point to the right of any point to the left on this interval, the point on the right will be higher. The function is increasing, the graph is going up. Over here, on this interval, any point to the right is lower than any point to the left. So we have here an interval of decrease. The graph is going down. Over here, the function goes back to increasing. So the function increases on this interval on the left, going up to -1. The function decreases on this middle interval between -1 and 1, from here to here. And then from 1 on, the graph goes back to increasing from 1 on. For some graphs, they stay constant in the middle somewhere. Now, in calculus, what normally happens is you start by determining the intervals of increase and decrease using the derivative, and then based on those intervals of increase and decrease, you can sketch the graph. So normally it goes in reverse. You determine these intervals first, and then that helps you sketch the graph. This uses the ideas of derivatives. When the derivative is positive, the graph's going up. When the derivative is negative, the graph's going down. If the derivative is 0, you're kind of flat, like over here. Next, we'll talk about some notation and a word problem.
Okay, so this will be a short end over here.
Hi, everyone. We don't always have y equals f of x. Be flexible. Sometimes we have h equals s of t. For example, let's say you go to the top of a building and you drop a coin at time t equals 0. Maybe high noon. Let t be the time elapsed in seconds since you dropped the coin. And really, it only makes sense for t to be non-negative in value. We don't care about your trip up the elevator. Let h be the height in feet of the coin, and let s be the position or height function. So we have h equals s of t. The height of the coin is this function of the time elapsed in seconds. All right. Also, now we don't care about negative values for t because we don't care about your trip up the elevator. Also, we don't care what happens after the coin hits the ground. Okay, so here, t, not x, is the independent variable. H, not y, is the dependent variable. And s, not f, is the function that relates, that maps values of t to values of h. All right, and we have the th plane, not the xy plane. All right, so again, at time t equals 0, okay, this is the height of the coin. It's with you at the top of the building, 256 feet. And then when you drop the coin, it falls. By the way, you can't see this in the sense that time is elapsing, right? The coin's going straight down. You're not throwing the coin at somebody. Okay. So you drop the coin, the height decreases, and then at time t equals 4 seconds, the coin hits the ground. And then in principle, the coin stays on the ground, but we're not going to worry about that. Okay, notice that the t and h axes are scaled differently. It would be a very awkward graph if they were scaled equally. Sometimes you're kind of forced to do that. All right, in the homework, you'll discuss this in further detail. So, graphs of functions.
All right, very good. So that's all regarding the lecturing. I did want to have some time for discussion today.
The network, I think I lost the net.
All right. So at this point, I'll open up for questions, and we'll do more of this on Thursday, of course, and we'll continue with chapter 1 also. So we'll have a bit more then. Actually, 1.3 on the gallery of graphs. That's a really interesting, important lecture that will save you a lot of time. So even if you don't have too many questions on the homework, 1.3 is going to be a really, really. I'll erase this. Really, really important section. Okay, so 1.3 is going to be very important. All right, so that's all for today. I will take questions. The whole point was that I was going to take questions. Any general questions before we hit the homework questions? Any general questions? Okay. Yes, you're welcome. Yeah, and if some of you need to leave, that's fine. I was going to take the remainder of time for questions. All right.
I have a question.
Okay. Okay. Now, by the way, I'm still recording, but then if people want me to stop recording, I'll stop recording. So are you okay? Are you okay with the question now?
Yes.
Okay. Go ahead.
So my question is, for the homework, it's only chapter 0, right? That's due?
Homework's only chapter 0, which is due Friday.
Okay. Friday by midnight?
By midnight, yeah, 11:59 p.m. basically midnight, right?
And we have to email it, right, to you?
Yeah, email it to me, or you could do Canvas, but email is probably easier, more straightforward. Of course, it would be electronic. Don't like snail mail it to me or anything.
Okay, thank
Yeah. You should know my address anyway. All right. You're welcome. Yes. Okay. So anything else before I stop the recording? Like, for example, if people would like me to do a question from scratch, that could be for the benefit of all the students. Anything else before I stop the recording? Okay, so I'll stop the recording. And this is why on Thursday, I'm expecting that I'll have 1.3, and then I don't think I'm going to get too much recording of student questions. But that's okay. That just means it'll be the Zoom class, basically. All right, I'll go ahead and stop the recording now.